All right, problem 5 says a city's population S follows the model S equals P times e to the RT. The value of P is the city's initial population at time t equals 0, and the number R is called the annual increase factor if R is positive, or decrease factor if R is negative. And part A says if a city had a population of 1.2 million in the year 2000, so that's when t is 0, and the annual increase factor is 7%, in what year will the city's population double? All right, so we're told that P is 1.2 million. This is our initial population, which is in the year 2000, and our annual increase factor, R, is 7%. So as a decimal, that'd be 0.07. Okay, so we have that S then is 1.2 times e to the 0.07t. And so now if I'm going to double the population, so double the population would be when S is 2.4. So we'll set S to 2.4 and then solve for t. So much like what we saw in the last video, okay, I'll start by dividing both sides by 1.2 to isolate the exponential term. And that's going to give us a 2 on the left and our exponential term of e to the 0.07t. And now we can write this exponential equation as a logarithmic equation. So I'm going to get that the exponent 0.07t, that's equal to the logarithm, and here it's a log base e, so I'll write that as ln of this number 2. Okay, so then finally dividing both sides by 0.07 tells us that t is the natural log of 2 divided by 0.07. If you use your calculator, you're going to get about 9.9. Okay, so keep in mind, right, t equals 0 corresponds to the year 2000. So we're saying that the population will double 9.9 years later. So this would happen then towards the end of the year 2009. Okay, we're not quite to 2010. All right, cool. So how about part B? It says if a city had a population of P in the year 2000, so again, that's when t is 0, and the annual decrease factor is 5%, in what year will the city's population have? All right, so notice they don't give us a numerical value for P. They're just telling us that it's some number P. But they do give us the annual decrease factor, and that is, in this case, it'd be negative 0.05, because the problem states here is that if it's a decrease factor, okay, then your R value is negative. So that's going to tell us that S is equal to P, which again, I don't know the numerical value for that, times e to the negative 0.05 t. All right, and we want to know when the city's population will have. So have population. So that's when S will equal half of this starting population, which is P. So I want S then to equal P over 2. So I'll set S to P over 2 and set that then equal to P times e to the minus 0.05t. And notice if I divide both sides by P to isolate my exponential term, these P's are going to divide out. All right, so what is that going to give us? We'll get just a half on the left-hand side, and on the right we have just our exponential. And now let's go ahead and write that as a logarithmic equation. So this exponent, negative 0.05t, that's going to equal the logarithm, and it's a log base e, so I'll write that as ln, and we're taking the natural log of a half. All right, so then to finish, we'll go ahead and divide both sides by negative 0.05 to get t on its own. And so we see here that t, which is, and I'll just move the negative in front, so minus this ratio of the natural log of a half divided by 0.05. Okay, this is going to be what? Well, let's go to the calculator. So minus, we want the natural log of 1/2, and then we're dividing by 0.05, and we get about 13.9 if I round a bit there. So again, since the year 2000 is when t is 0, and we're saying that the population will have 13.9 years later, okay, this then will happen in the year 2013. So we're not quite to 2014. Okay, and what's interesting about this result is that it's totally independent of what your starting population is. So if your starting population was 1.2 million and your population is decreasing with this decrease factor of 5%, then your population is going to have in the year 2013. But let's say your city had a population of 100,000. Well, it's still going to take that same amount of time for your population to have. All right, cool. Well, that'll do it for this problem. Thanks.